Welcome to this Tutoring Center video. Follow us on social media if you'd like to. I'll be presenting today. Today we're going to talk about solving a second order circuit. Let's solve this second order circuit. First, we will draw the circuit right before the switch is flipped and find the voltage across the capacitor and the current through the inductor. We find these values because we know that immediately after the switch is flipped, the capacitor voltage will be the same as it was before the switch was flipped, and likewise for the inductor current. We assume that the circuit is in steady state right before the switch is flipped, so we draw the capacitor as an open and the inductor as a short. We can simply use Ohm's law to see that the initial VC is 10 volts and the initial IL is 1 amp. We will need to use these values later on. Now let's draw the circuit at t equals infinity, or after the circuit has reached steady state again. Once again, we draw the capacitor as an open and the inductor as a short, but without the voltage source, since the switch is open and the voltage source is therefore disconnected. From the drawing, we can quickly see that there will be no current and no voltage, so VC at infinity equals 0 and IL at infinity equals 0. We will need these values later on as well. Now we will draw the circuit after the switch is flipped. We have a single loop, so we will set up a KVL equation. At this point, we will need to remember the equations for voltage across a capacitor and an inductor. These are good equations to have written down on an equation sheet of your own. Once we have the KVL equation, we take the derivative of both sides. Then, let's divide both sides by L to get the differential equation into this familiar form. We will now use what we know from differential equations to solve for the roots of this second order differential equation. That then leads us to our parent function, seen here. If this step is unfamiliar to you, then I recommend reviewing second order differential equations with constant coefficients. Now that we have our parent function for I of t, all we have to do is find the three constants, k1, k2, and k3. After that, we will have our solution. Let's start by finding k3, since that is the easiest one to find. We can find k3 by plugging in infinity for t and using the value for I of infinity that we found earlier. Doing so shows us that k3 equals 0. To find k1 and k2, we will need to get two equations and solve the system of two equations. Let's get the first equation by plugging in t equals 0 and the initial current value we solved for earlier, which was 1 amp. Plug those values in and simplify to get our first equation, 1 equals k1 plus k2. Now we have one equation, but we need two. How do we get our second equation? This is the hardest part and the part that everyone forgets. When you get to this point, you want to do the same thing every time, and that is this. Take the derivative of the function you have. You will see why in a minute. The function we have is IL of t equals k1 e to the minus t plus k2 e to the minus 4t. So we will take the derivative of that to get IL prime of t equals minus k1 e to the minus t minus 4k2 e to the minus 4t. Now how is that going to help us? Well, let's recall the equation for voltage across an inductor. VL of t equals L times IL prime of t. Again, this is one of the equations you should have written down on a reference sheet. Let's use that equation to get our second equation. Remember that our L value is 2, so we have VL of t equals 2 IL prime of t, which gives us VL of t equals negative 2 k1 e to the minus t minus 8 k2 e to the minus 4t. We now want to plug in t equals 0 and use the value for the initial VL. But what is the initial VL? To find that, let's take another look at the circuit just after the switch is flipped. We know that the inductor is like a short right after the switch is flipped, and the voltage difference across a short is 0. Therefore, VL of 0 equals 0. Now we can plug in t equals 0 and VL of 0 to get our second equation, giving us 0 equals minus 2 k1 minus 8 k2. Now we finally have our two equations with our two unknowns, k1 and k2, so we can solve the system of equations. When we solve the system for k1 and k2, we can plug those values into our original inductor current equation, giving us our final answer.